Okay, so today on the agenda for today, we are going to cover two things quickly. Example 2.1. It's the first example. Very straightforward. And the second thing we will do is complex power. Complex power. All right, let's get started. So, example 2.1. So example 2.1, they gave you something like this, if you remember. Some time varying voltage and time varying current and the load, and it's something like this. And then they tell you, okay, voltage, which is a function of time, is 100 cosine of omega t. And they tell you that the current, which is a function of time, is 1.25 with an angle of 60 degrees. My bad, it's the impedance. They tell you this is the impedance, ohms. Right? And now, the next thing they want you to do is they want you to find the current, and they want you to find the instantaneous power. So to find the current, you say, okay, everything has a magnitude and a phase. So if we look at the voltage, the magnitude is 100. What's the phase? Nothing, right? Because there's no phase. Then we divide it by the impedance. Impedance is 1.25 with an angle of 60 degrees. What does this work out to when you punch it in your calculator? It becomes 80 with an angle of 0 minus 60, so minus 60 degrees. Yeah? Amps. And then you can say, okay, this is the same thing as this. 80, and you multiply that, which is the representation of this, and then you multiply that by 100 cosine of omega t, and that should give you power as a function of time. And you can say that power as a function of time is equal to 8,000 cosine omega t, without doing any expansions, cosine omega t minus 60 degrees. Now I'm not going to do the expansion because they didn't do it in the textbook. So that's pretty much it. That was it for this example. That's all they wanted you to know, essentially. Okay, so now let's talk about complex power. I'm going to try to save you time here and not try to go too much in depth in what they're saying and basically tell you what the main thing is. But basically, if you've got any voltage, you can represent it as a magnitude, and it's got some phase, theta v. Similarly, any current has some magnitude, and it's got some current, some angle, I should say, theta I, and graphically that looks something like this. You've got a real component and you've got an imaginary component, and then essentially if you have this supposes your voltage, this supposes your current, has a phase of theta v, and this one has, you can say it has theta I, and the angle between these two are theta, where theta is equal to theta v minus theta I, yeah? And they also call this the impedance angle. Now, another thing is, yeah, so basically what the main thing that they want you to know is that the parent power is equal to conjugate of the current multiplied by the voltage. Yeah, conjugate. This is important because what's going to happen is in other examples that we will do, you're going to have some voltage, you're going to have some impedance, you're going to divide it normally to get your current. That's not a problem. Then you multiply that current by your voltage, and you're going to get some answer. You're like, what the hell? Why is it not giving me the right answer? Well, that's because you have to conjugate the current value. So what does that mean? So if we have some value of 100 with 60 degrees, suppose this is my current, the conjugate of that will just be 100 again, but just minus 60. Similarly, if you have 5 plus 6j is your current, what's the conjugate of that? It's going to be 5 minus 6j, right? That's all. And then you just multiply normally with your voltage, and you get your apparent power. So that's basically it for that. Why do we care about apparent power and real power? I will go into more detail, but basically a power company has to care about apparent power because it does affect how much current they have to pump out, because it's something that's they still have to supply, right? And like if you have factories, usually this only applies to factories, is that sometimes they've got inductive loads and stuff like this, and then that actually really matters, and they have to charge them more for that. Usually they install capacitor banks, the power companies, all around the grid to try to compensate for that. We will talk about power factor compensation later, and we'll do some examples on that. But for the residential, usually they only charge for real power because it's not really, there's not that much of apparent power, very little that's used on the residential. Yeah, so that's pretty much it. It goes into a little bit more depth here. I can write down some formulas here. But yeah, I can write down some formulas. You know that S is equal to P plus QJ. This is just repetition. Magnitude of this is P squared plus Q squared, square root of that. They give you some formulas. Pretty much, that's basically what we talked about here. You know that when theta is less than 0, what does that mean? What does that mean? Okay, so what is theta? Theta is theta V minus theta I, right? So if theta is less than 0, that means that the current angle is more than the voltage angle, which means it's shifted more to the right, which means that the current is lagging. If the current is lagging, that means that the voltage is leading. If the voltage is leading, that is capacitive. That is capacitive. That's just another thing, I guess, that they sort of emphasize in this section, and that's about pretty much it for this section here. Pretty quick video. That's all I got.